This is going to be the lecture over additional proportional problems. So let's get to it. All right, we're going to be looking at number one here. If the dose rate is 205 centigrade per minute at 80 cm, what is the dose rate at 67? Let's take a look here. All right, so get my trusty pen working here. And get it to work. All right. So now, what are we looking at here? We're, again, remember that we're going to be flipping back and forth here in these problems between dose rates and distances. Now, the difference is going to be that if you're dealing with a dose rate, you're going to be looking at squared distances. If you're looking at just diameters, in that particular case, you're going to be looking at just doing similar triangles, which means that the distances aren't squared. So something to bear in mind here. So we've got 205 centigrade. We don't know what the dose rate is at the other. But what we are looking for here is, we know this is at 80 cm. And so we're looking at it for 67. So the question, the reason these are flip-flopped is because when we're dealing with doses, those distances are they're changed around. It's not like similar triangles where you keep the same length on top and the same length on the bottom. In this particular case of the dose rate, it's going to be changed around. So we don't know what the dose rate is here, but we know that since we've got a certain dose rate at 80, if we're moving in closer to the source, then this should end up being higher. Now, if we go through and we move the x over here and move the fraction over here, what we're going to end up with is 205 centigrade, and technically that's centigrade per minute, times x is equal to 67 over 80 squared. Multiplying both sides by x means that they cancel over here, which gives me 205 centigrade per minute is equal to 67 divided by 80 squared times x. In order to get rid of this term over here, what I'm going to do is multiply by the reciprocal. And that means over here gets multiplied by the reciprocal as well. So that means that we end up with x, oops, it's not squared, sorry. X is going to be equal to 205 centigrade per minute times 80 divided by 67. So if we are to go through and do the calculator, oops, I should just square that. There we go. Multiply that. Let's try this again. 80 divided by 67 squared times 205, come up with 292.9, or yeah, there we go. So Oops. Uh, 2.26 centigrade per minute. Okay. So now let's go ahead and let's clear all of that out. Let's go down to problem 2. Now, if a ring has a diameter of 16 cm on a film placed at 80 cm from a point source of radiation, what diameter will it have on a film placed 100 cm from the same point source? So our problem here, let's kind of draw this out. We've got a ring. We've got this going down here. I'm going to draw another line going from here down to there. And so we've got a ring here, and then we've got another one here. So we've got a point source here. So a ring has a diameter of 16 cm on a film placed at 80. So let me get back to the freehand drawing here. So we've got 80 cm away, and the diameter here is going to be 16 centimeters. Now, we're going to place a film that's going to be 100 cm away. What's the size of, or the diameter of that particular ring? Well, we know it is 16 at 80, but we don't know what it is at 100. And again, we're dealing here with distances. Distances are not squared, and we're working with similar triangles. So that's why we have the relationship here that we do. So if we do the cross multiplication of the 100, then what we end up with is 16 multiplied by 100 divided by 80. And what does that end up being? Well, again, let's go here. Let's take a look. Come on, 20. cm in diameter. Just check and make sure that I'm right. And I'm right. Okay. Clear this out. All right. So far, so good. 2 down. If the dose rate is 300 centigrade per minute at 105.5, then where is the dose rate 350? All right. So we're back to dose rates again. So let's see here. We've got this. So we're going to go here. So we got 300 centigrade per minute. And what we're wondering is, where is it going to be 350 centigrade per minute? Where? So at what distance? Now, again, remember, this is going to be dose rate. So it's not like the similar triangles where we have same side equals same side, and then same side equals same side, that kind of thing. Remember, these are going to end up getting flip-flopped. So we know that the 300 exists at 105.5 cm. Problem is, we have no idea where the other exists. So if we do cross multiplication, basically we square both the top and the bottom here. If we multiply both sides by 105.5 squared, do the same thing over here, 105 squared, This means, and let me see if I can clean this up just. So let's see. All right, so we've got 300 divided by 350 times, and the dose rates, the centigrade per minute will cancel. That's going to be multiplied by 105.5 squared cm. We take the square root of that garbage. 300 divided by 350 times 105.5 squared. What do we end up with? Well, let's find out. Go over here, clean all of this out. So I've got 300 divided by 350 is equal to that times 105.5 squared is equal to this. And then we take the square root of that. So come with 97.67. And there we go. Or 97.7. And that'll be CM 97.7. Sorry for the abysmal writing there, but that's what that comes out to be. All right, let's take a look here at number 4. If a ring is suspended 20, okay, this problem here was not written very well, or at least it's not clear. The ring is suspended 20 cm above a film. Now, what this should be telling you here, and is not, it's not clear, I know, because I worked through it and ended up making some mistakes here. So we've got the point source here, and the ring. I'm going to go ahead and put this in source, and then we've got the ring. Now, the distance from the source to the ring here, and then we also have the film, which is down here. The ring is going to be suspended 20 cm from the film. What this is trying to tell you is that the ring is 75 cm from the source. Here to here is another 20 cm. So we know that the ring is suspended 20 centimeters above the film. That ring is 75 centimeters from the source. What is the diameter if on the film it appears to be 12 cm? So we know that we've got 12 cm when it is 95 cm away. Let's see if I can write this legibly like a human being. Let's see. There we go. And let's try this again. $12 cm at 95. So what's the diameter? Or what is the true diameter if we have this going on? So we don't, it's actually 75 cm away. So that means that X is equal to 12 cm times 75 over 95. And that stands to reason this is less than 1. This is 12 cm here. So as we get closer to the source, it should actually be less than 12. Question is by how much? So let's go here, as we always do, to our trusty calculator. So we've got 75 divided by 95. And then we multiply that by 12. And we get 9.47. is this correct? I'm in suspense. 9.47. Okay. So then write this out here. So 9.47 cm. Okay. All right. Clear all that out. Keep scrolling down. If a probe reads an exposure rate of 120 centigrade per minute at some distance d, what will it read if the distance is doubled? Okay, this is a kind of a fun one because you don't have all the numbers that you might want in order to be able to plug into the simple calculation there, but that's okay. What we are looking at here is we know that at some distance d, the exposure rate is going to be 120. So let's see. So exposure rate of 120. So 120 centigrade per minute at some distance d. And we don't know what that d is, but again, we're dealing with dose rates here. So I'll put the big D right there. What will it read if the distance is doubled? I have no idea what the rate is, but I do know that over here, the distance is in fact doubled. Since we're dealing with a dose rate, we're going to end up having to square this. Now, it's a funny thing because when you take twice of something divided by that same something, you get just a number. So you get 4. So doing some cross multiplication, if I've got 120 divided by x is equal to 4, multiply both sides by x, and then divide both sides by 4, you end up with 30 is equal to x, and that should be in centigrade per minute. Now, am I right? I could be lying to you. But as it turns out, I'm not. Okay. All right, so now let's go down. Let's take a look here. Number 6. How far away from radiation source must a film be placed if a ring of some diameter d, which is 95 cm away from the radiation source, is to form an image which is twice as large in diameter as the original ring? All right, so again, we're back here working with similar triangles because we're dealing with distances. So how does this all work out? So here we have, let's see, the distance d is at 95. What we are looking for is what distance we're going to find. I can't do this for a spin. Let's see. There we go. We don't know what that distance is, but we can figure it out. So we rearrange a few terms, cross multiply here and whatnot. We end up with d divided by 2d times 95. The d's cancel. Whoops, got that wrong. Sorry. Let's try that again. So we end up with x is equal to 2d divided by d times 95. Should be 180. I'm sorry, not 180, 190, because I can't do math. Annotate, erase, 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 erase. Let's try this, because 95 times 2 is in fact 190. There we go. All right. Now, let's go down here. A patient is set up. Now, there's a lot of cobalt 60 in these problems. And, I understand that most therapists, when they get out today, are rarely, if ever, going to work on a cobalt unit. However, they do make for some nice similar triangle problems. And on top of that, get you to understand the relationships between dose rate as well as similar triangles and things of that sort. So they do have their usefulness. So let's take a look at this again. If a patient is set up on an axis on a cobalt 60 unit, the AP field size on the skin is 12 by 7. Now the patient is 17 cm thick in the APPA plane. Isocenter is considered to be midline. What is the AP SSD and what is the field size at the isocenter? Now, if you're going to be looking for the AP SSD, what you need is you've got all the information you need here in order to be able to compute that. Now, for cobalt 60 units, isocenter is going to be at 80 cm. Now, we know that we've got our patient here, and I'm going to say this is the anterior and this is the posterior. Now, our patient, cut him down the middle, which is not recommended, but if you do that, then this distance right here, which is 17, means that when you cut it in half, you've got a segment from isocenter to the outside, which is 8.5, and then you've got one running from the isocenter to the posterior, which is 8.5 cm. So if you're looking for the APSSD, what you should do is take the isocentric distance, subtract 8.5, and you should come up with 71.5 cm. So that's your APSSD right there. Now, what is the field size at the isocenter? We know what it is at 71.5, but we need to figure out what it is at the isocenter. So we know this is what's going on at the APSSD. I don't know what this is at 80, but if I do the proportions, what do I come up with? I got 13.42. And usually in most cases now, with most accelerators, you're only going to have the field size down to 1/10 of a centimeter. So abbreviate, that's 13.4 cm. Same thing goes for the other dimension. Problem is going to be set up, and I'll change that. Let's just change that to Y. This is Y. So we've got 80 cm. So Y is equal to 7 cm times 80 divided by 71.5. Y turns out to be 7.8. Wait, did I say 71.8? I don't think I meant that. I think I meant 7.8. I'm sorry. All right, try that again. Okay. There we go. All right. So let's clear all of that out. Go down to the last problem here. The dose rate at 80 cm from a cobalt 60 unit is 110. At what distance is the dose rate 75? So again, we're back to dose rate. Yay. So how do we write this out? Our dose rate, we know 110 over 75. And again, dose rates per minute. And what we do not know is where it is at 75. So we put this stuff up there and we do that. So we end up with x squared is equal to 110 over 75 multiplied by 80 cm squared. Not exactly sure what that's equal to, but if you take the, we'll go through those here on the calculator. 110 divided by 75 times 80 squared is equal to that. Now, to find x, I have to take the square root of that. So I end up with 96.88. Let's do the final check here. 96.80. Okay. All right. I hope you got something out of this.